Everyone is ready? Okay, great. Okay, let us start. Okay, today's topic is amortized analysis. Okay, I've picked the analysis, the definitions from Wikipedia for amortized analysis. So amortized analysis is a method for analyzing a given algorithm's complexity or how much of a resource, especially time or memory, it takes to execute. Okay, the motivations for amortized analysis is that looking at the worst case is too pessimistic. Instead, amortized analysis averages the running time of operation in sequence over that sequence. So in other words, how we analyze amortized analysis is by getting the total, for example, in terms of time, we will be getting the time complexity, and then divide by the total, divide by n. There are few methods to perform amortized analysis. We'll be looking at the aggregate methods. So these aggregate methods are the methods you are more familiar with. So it's similar to how we do the how we calculate the time complexity that you have learned so far. Okay, so we'll look at an example. This example is from your reference. Okay, so the problem is called the expandable array problem. Okay, so most of the array, as you know, is cannot be expanded, but this is a expandable array problem. And what does it mean by expandable array? Expandable array is an array that can expand. Okay, so meaning as you know, an array has when you initialize an array, you set a specific size and then you initialize, right? So, and if you use up the whole array to store values, right? Then you cannot store more than the size of the array, right? But this expandable array, you can expand it. Okay, you can expand it. So when the array is full, then we can expand it. So there are a few ways to expand the array. We'll look at two methods to expand the array later on. Okay, so here in this figure, we have examples of how we could expand the array. So if you look at the figures, we have A, so gray out meaning the array gray out meaning they are fully is already filled. So we create another array B, twice the size of array A. Then we copy the items from array A to array B. After that, we dereference. Okay, look at the letter A and B. Now B become A. Okay, then the initial array A will be then removed. Okay, so basically these are the steps, and on the right you see are the pseudocodes. Okay, on the right are is the pseudocodes. Okay, so okay, look at the codes. If t is equals to length minus 1, meaning it's already full, then you create a new array B. Okay, how this it doesn't specifically spell out how to create array B of what size, right? But we create an array B of in this example, then it will be twice the size. Okay. Then after that, there is a for loop that will copy the items from A to B. So it's equivalent to the figure B. Okay, figure B over there. And then we dereference. After we copy all the items, we move we set item array B as A, right? Sorry, my screen has some problem. Okay. Okay. After that, then we'll continue. If there's a new item to add in, then we'll just add in as usual. Okay. So if you look at the algorithm, for most of the time, okay, for most of the time, when you add, when you are adding something into the array, the time complexity of it is take constant amount of time, right? When we want to add an item to the array, it takes constant amount of time because we are only executing the statement at the bottom. Okay, the we only execute two statements at the bottom, which is n equals to n plus 1, and then we insert item E to the array A in position n minus 1, right? So most of the time, you will notice that when we insert an item, it takes constant amount of time. But there is some certain moment it takes more. Okay, it takes more, right? So when is that moment? The moment is when the size of the array the array is full, right? When the array is full, then we need to create a new array and then copy the array from copy the item from array A to the new array B. So if you look at here, right, we need to initialize an array. Obviously, this should take constant amount of time normally. Then there is a for loop to copy item A to the new copy items from array A to the new array B, right? So this is a for loop, and as you know, right, this for loop start from item 0 until n minus 1, meaning it will be running n times, right? So at certain moment, okay, at certain moment, when we add item, you can see that it runs n times, right? The time complexity is big O n over here, right? Big O n. But at most of the time, okay, at most of the time, these add operations take only constant amount of time. So that is why why we do this amortized analysis. Okay, the amortized running time of operation within a series of operation is the worst case running time of the series of operation divided by the number of operations. So we want to know on average how is it, okay? On average, how is it? Okay, over here also, amortized analysis consider both costly and less costly operation together over the whole series of operations of the algorithm. Okay. So there are certain times it is more costly, especially when the array is full. So we need to create new array and then copy item from array A to array B, right? So this is the more costly operations. But most of the time, the operations take constant amount of time when we add. So we want to know through amortized analysis on average to what's the picture. Okay, so we want to know on average the add operation or what's the complexity, right? Okay. So first we'll be exploring two strategy. One is called incremental strategy. Okay, in incremental strategy work just like what I mentioned just now. Okay, when the array is full, we create a new array which is twice the size of array A. Okay, twice the size of array A. So here what we explain is the aggregate method. Basically, is just like how we did the analysis for time complexity. Okay, that you have learned. So what we will do is find out the time complexity of the functions. Okay, and then calculate and then divide by n. Okay. Okay. Let us look at the cost of. Let us look at the cost of doing the copy operations. Okay, doing the copy operations. Okay. Initially, our array has. Okay, look at this array simulations. Initially, our array has a size of 4. So we assume the initial size is 4. Okay. So when initially, then what we have an item, we put it at the position 0. Okay, position 0 of the array, right? So what does it mean? Meaning the time, as I mentioned just now, is constant, right? If you look at the code, it takes constant amount of time. So for constant, we will just use 1 to represent. Okay, we will just use 1 to represent. If you want, you can use 1. You can use 1C if you want, but oh sorry, yeah, you can put a C there instead. Okay, if you want, you can put a C there to represent constant, or here we just use 1 to represent constant. Okay. So if you have the first item, so the cost is 1. The second item, the cost is 2. The third item, the cost is 3, right? The fourth item is the cost is become 5. So why become 5? So when we have put the fourth item, now our array A is already full, right? Our array A is already full. Then what happens is we create a new array. Okay, we create a new array, right? And then we copy the items. Okay, we copy the item from array A to the new array B. So this longer one is the new array. So we add 1 plus 4. That is why we get 5. Okay. So what you see here is like what I mentioned just now. So for most of the time, the cost of the add operations is take constant amount of time, right? But when we reach the max capacity of the array, then we have to create a new array, okay, and then copy. Okay, so now here we have 5. Okay, so this is how we get 5, right? Okay, next after that, if we increase after that, if we insert more item into the array, right? Okay, so let me see your comment. Okay, okay, no problem. Okay, so here is 3 plus 1. Okay, So here is we add this one is 1, right? And then we copy every item to the new array. So 1 plus 2 plus 3 plus 4 plus, sorry, 1 plus 1 plus 1 plus 1 plus 1 is 5. Okay? Can? Okay. So now our array has a 8 size of 8 already. So when we add another item, so now it back to cost 1, right? The cost is 1, constant. And then add another one, add another one, add another one. Now again we reach the max capacity of this new array, right? So when we reach, by the way, I didn't do all, I just do some of them, okay? To let you see the sequence, okay? To let you see the sequence. When we hit this one, when we hit this one, right? What happened? Okay, let's say we hit this one. So if we plus 1 over here, okay, we plus 1 here, plus 1, just like just now we plus 1. And then what else? We have to copy to the new array, which is twice this size. So that is why the cost of this is 9. Okay, you have to copy all the items to the new array. Okay, so okay, now let us analyze the cost. Okay, let us analyze the cost. So if you analyze the cost, let us take all 1 out. Okay, take out all the 1, cost of 1. So there are how many 1? There will be n. There will be n1. Okay, there will be n1. So if we take out 1, if we take out 1 from here, then this becomes 4, right? This, what I meant is we split this cost to 2 parts. Okay, we split this cost to we split all the costs here to 2 parts. One part is consists of 1 1, all ones. Okay, how many 1? There will be 5 1. Okay. And after we take out all the 1, then this becomes 8. So why I do this? Just to show you the analysis. Okay, to show you the analysis. This becomes 4. This becomes 8. This becomes 12. Right. So how many 1 there will be n? How many times of 1 there will be n times of 1? So we have 8, 4, 12. So the sequence that you see will be 4, 8, 12, 24. So we can change it to this form: 4 times 1 plus 2 plus 3 plus until n. Okay. So we see this sequence before. So this sequence is n times n plus 1 divided by 2. And this k is this 4 is actually k, right? 4 is actually k. So total up Tn is n plus this k n times n plus 1 divided by 2. Okay, any questions? This is the example. Okay, this is the example, right? This is the example. Okay, I explain again. Okay, I explain again. This is the array simulations. Okay, array. Okay, can you see it right now? So okay, so this this is the cost of the add operations. Okay, this is the array simulations. So initially our array has the size of 4, or initially our array has a size of 4. So when we insert item, we'll insert it here, right? So the cost is constant, is a constant, right? The cost is constant. Why is constant? Look at this algorithm. When it is full, only you have to create a new array, and then when it is full, only you have to create a new array, and then copy the items from A to B, and then remove the earlier A, reassign B. Okay, we only need to do that when A is full. If A is not full, we just add as usual, and if we add as usual, you see, this is the only part. So this is a constant. So constant, normally you can use C or some other character, or we just say it is 1 to represent constant, right? Okay. So when like what I mentioned just now, so this is our array. So when we first enter our array initially is empty, so we put in an item, so it take constant amount of time. So we put 1. We put another item 1, another item 1, another item. Now we reach the maximum capacity of the array, right? So what we need to do, create a new array twice the size, and then copy the items. So the first cost is that incur is this one, right? Cost 1. And then next we will copy the items. Okay, we'll copy the items to the new array. Okay, we'll copy the items to the new array. Okay. So now we have a array A. Okay, this array A. Okay, now this array A has 8 items. So when we have new items, again we add. Okay, we add to the position 5, position 6, and then position 7. And if you put in one more item, then our array will become full again, right? When it becomes full again, what happens? Next is we create an array which is twice the size. So this time our array has how many items? Yeah, minor, thanks. So our array has 16 items right now. So after we create the array, what is next? We have to copy the item one by one to the new array, right? One by one. So there will be 8 items, right? There will be 8 items plus 1 just now we add. So 8 plus 1 equals to 9. So that is why we get 9 here, right? Okay, now we have a new array. So this is our new array again. So this one is already removed. Okay, so this is our new array. If we add more items, then if we add the next item, then it will become 1 again. Okay, it will become 1 again, right? It become 1 again, right? So 1, 1, 1. Then oh, sorry. Actually shouldn't be 16. This is increment. Okay, this one is increments. Increment strategy. You increment by 4 every time. Okay, sorry, I made a mistake. So every time you increment 4, 4, 4, 4. That's what happened here, right? So next time we add, it will be 1, 1, 1 until we hit this one, right? Size 12. Okay, when we hit size 12, then it will be full again. So this is not right. So the initial array has a size 4. Next the next time we expand the array, become 8, and then we expand again become 12. Okay, so this is increment approach. Okay, this increment approach where it increment some number of k times. Okay, some number of k times. So okay, so we do amortized analysis to see what is the average cost of the add. Okay, at the add operation, because if you just look at this, it's hard to know, right? Because most of the, if you look at most of the operation is like it's constant, but there are certain operations that which is more costly, right? Which is more costly. Okay, so how to analyze this cost here? So to analyze this cost here, we break this to 2 parts. To make our analysis simple, we break this to 2 parts. So we take out all the 1 out, 1, 1, 1. If we take out all the 1, then this 5 becomes 4, 9 becomes 8, 13 becomes 12, and then this one 17 becomes 16, right? Okay, so if we take out 1, 1, 1, then there will be total n1. Okay, there will be total n1, right? Okay, so then if we take out all 1, then this becomes 0, this becomes 4, right? This becomes 8, this becomes 12, and then 16. Let us look at this sequence. Okay, 4, 8, 12, 24, and so on, right? And so on. So we change it to 4 multiply. We take 4 out. Okay, we take out 4. That will be 1 plus 2 plus 3. So 1 plus 2 plus 3 plus until n, right? So we have learned this sequence before. This sequence will be equivalent to n times n plus 1 divided by 2, right? And this 4 is actually k. Okay, 4 is actually k, right? 4 is actually k. Okay, so this is the Tn, right? Okay. What is the question from Raji? What is the time complexity of creating a new array? When the existing one full, then copy the elements in the old array into the new one. Yeah, so okay, so creating the array actually take constant amount of time also. Okay, creating an array also take constant amount of time. Okay, and then the other cost is to copy. Okay, to copy the items. Okay, to copy the items. To copy the items from old array to new array. So that is the cost. Okay, the red one is the more costly operations of the add. Okay, the more costly operations of the add operations when the array is hit the maximum capacity. Okay, so if you okay, so if you look at the this approach of the how we increment the array, so we get Tn is this, right? Tn is this. So the amortized time is equals to the Tn divided by n. So So this is the cost. Okay, so this is the amortized time. Okay, this tells us that on average the cost is big O of n. Okay, big O of n. Why we do this analysis, as I told you earlier, if you look at some of the cost is constant, but some of the cost is very expensive, right? Some of the costs are very expensive. So we want to know on average, this add operation, how expensive it is. Okay, on average, how expensive it is. Okay, so what I explained just now is how we increment the array. We increment the array in we expand our array in incremental approach. So we increment k every time. Okay, we expand our array to k every time. Okay, k plus k every time, plus k every time, right? Now, okay, now we look at a different strategy to expand our array, which double our array every time. Okay, so okay, so this is the expandable array problem by doubling our array every time. In this approach, we start with array of size 1. Okay, our initial, sorry, this is wrong. Our initial size is 1. Okay, our initial size is 1, right? So we put one item in. So we put one item in. Now is already full, right? Now it's already full. So we create a new array and then copy the items there. So we write is cost 1, then we copy 1, right? So that is why we get 2. Okay. So this is our new array, right? New array. So okay, we put one item in. Now again, our array is full. We double our array. 2 become 4, right? And then we copy the items into the new array. Copy it over. Okay, copy it over. So here is 1 plus 1 plus 1. So this is how we get 3, right? Now this is our new array. The old array removed, right? Okay. So now we enter items. Okay, item to our array. So the cost back to 1 again. The cost back to 1 because it's not full yet. Then we put another item. Now okay, full again. Okay, full again. Double our array. Now 4 become 8. And so this is what cost 1, right? And then we have 1. And then we copy 1, copy. So 4 copy plus 1 insert, right? So total 5. So this is how we get 5, right? So now this is our new array, right? This is our new array again. Now when we enter items, we enter it here. So still haven't reached the maximum capacity. So it's 1 here. So if you put another item, so it will be 1. Put another item, it will be 1. Put another item, now full again, right? Now we will have to expand our array to size of, okay, size of 16. Okay, so this is doubling our array every time. And then we copy copy all the items over. So the cost now become 17, right? cost is 17. So now, what is the total cost? Okay, what is the total cost? We want to find out what is the total cost of these operations. Okay, total cost. Okay, for this, again, we break this to two parts. We break up this to two parts. We take out all the one. Okay, we take out all the one, and then so these two become one. These three we minus one to every value. Okay, we minus one to all to every value because we take out all one. If we take out all one from this array lah, then there'll be n1, right? There'll be n1, and since we take out all one from this array, so now 2 become 1, 3 become 2, then this becomes 0, this is 4, this is, then this 0 0, then 8 0 0 0 until then 16 and so on, right? So the second part consists of the sequence 1 plus 2 plus 4 plus 8 plus so on. Okay, so this sequence, okay, so this sequence can be proved to be 2n minus 1. Okay, 2n minus 1 geometric series. Okay, geometric series, k is equals to log n. Okay, this k is not equals to n, k is equals to log n. Okay, so this can be proven equals to 2n minus 1. Okay, so 2n minus 1 plus this n is equals to 3n minus 1. And the amortized time basically is just divided by n. So what we get is big O1, meaning this is considered constant, meaning the doubling strategy is better than the incremental strategy. Okay. So in amortized analysis, we end in this example, we see that there are most of the time you see the cost is constant, but there are certain time when the array is full, then we have to copy items over, right? So you see the red square is the place where more costs, okay, more costs, or more operations have to be performed. Okay, so through amortized analysis, we can know on average the add operation, how costly it is. Okay, how costly it is. For incremental strategy, each add operation, the complexity is big O(n) on average. Okay, big O(n) on average. And for the doubling strategy, on average, the amortized time is considered constant. Okay, consider constant. Okay, on average. Okay, on average. Okay. So this amortized analysis is interesting. It's interesting for us to know on average and operations. Okay, of, for instance, the function, how costly it is, right? Okay, so we have about 1 more hour. We'll go to a different topics. Okay, we'll go to a different topic. we'll go to a different top. We'll discuss the new topics, but it is still analyzing the time complexity. Okay, we'll still be analyzing the time complexity. The slide is at which one? Yeah, the slide is at e-learning. The slide is at e-learning. You can get it from e-learning. Amortized analysis, yes, is the slide is actually at the topic of amortized analysis is actually at the end. Okay, it's at the end of the slide the slide last week that we discussed. Okay. Okay, if you look at the front, it's actually at the end of the slide yesterday, not yesterday, the slide last week that we use. Okay. Okay. Now we look at another interesting topic in analyzing algorithm. So now we are looking at recursion. Okay. Everyone here, anyone here doesn't know what is recursion? Anyone does not know what is recursion? Everyone knows, right? Huh? Sopti, you don't know? Recursion should be either you are not computer science, then it makes sense you don't know what is recursion. Recursion or recursive, okay, what is recursive? Recursive basically is a method calling itself. Okay, the method calling itself is called recursion. Okay, so loop. Okay, in when we analyze algorithms, right, we saw loops, right? Loops, for loop. It can be for loop, while loop, different types of loops. Okay, so why loops? Why loops is important in analyzing algorithm? Because loops repeatedly do certain things, right? It helps us to do things repeatedly, for example, n times. Okay, so we can do things repeatedly n times using loop. Another way of doing things repeatedly n times is using recursive call. Okay, recursive call. So for those maybe not which is which has no background in computer science, or then probably you may not be very familiar, but it's not difficult. The concept is not difficult. Okay, so in this example, for instance, we have two snippets of codes. Okay, we have two snippets of codes. One code, basically, what it does is just add 5 every time to a variable with an initial value of 10. Okay, so it adds 5 every time. Do it for n times. Okay, do it for n times, right? So we already saw, okay, analyzing algorithm like this is with a loop considered to be not very difficult, right? So what's the time complexity for this piece of code? What is the time complexity for this piece of code? Thanks, Raji. So it is not difficult to show that this piece of code is n because this is 1, right? This part is n, right? This part is n. So if you write a function n, right, you can count, right? For example, how many times the initialization, how many times the addition, how many times the comparison, and then addition and then comparison around 5. I think 5n plus 1. Okay, around that. Okay, so and then from there we can find out the big O, right? Okay, for loop is quite easy. Okay, for loop is quite easy, but another way of sometimes instead of using loop, we might want to use recursive call to do repeatedly. We want to do certain things repeatedly through recursive call. Okay, recursive call basically is a method that call itself. If you look at the name of the method or functions, they are the same. Okay, they are the same. These two pieces of code, one using loop, another using recursion, they do the same thing. Okay, they do perform the same thing. Basically, it adds 5 every time. Okay, it adds 5 every time. And then if look at the recursive method. If I less than n, then we'll execute this statement. We'll call recursive and then increment I plus 1, increment j plus 5. Okay, increment j plus 5. So initially I is equals to 0, right? J is equals to 10, right? So now if I let's say n is we put it like we put it like 3 lah, for instance, right? Let's say we put it as 3, right? So I is 0, so this is true. So now we increment I become 1 plus what, because I plus 1, right? I plus 1 is 1. J is 10 plus 5, now become 15. So now we go back to the functions recursive and then execute again. So now I is 1 is still less than n. You call it again, right? So you can trace you can trace the value. You can this is I, right? This is j. So it's 0, 10, then 1, 15, right? And then 2. What I'm trying to do is tracing I and 0, right? And then 20, right? Right? Then 3. The moment we hit 3, right? What happened? This statement here become false, right? Then we start to return j, which in j, sorry. So the moment we reach 3, then we return j. J is 20. Okay. I hope I add it correctly. I trace it correctly. Did I? Or 25. Okay. Please try to trace it. Okay. On your own. I think should be 25. I think should be 25. Okay. So this basically do what the loop do. Okay. This basically do what the loop do, but through recursive call. Okay, through recursive call instead of using a loop. Okay. So why? Okay. So we saw that through loop analyzing the complexity is considerably easy, but for recursive call, it could be more complicated. Okay, slightly more complicated. Okay, for this one still okay. Okay, later on we'll see some examples that that is more slightly more difficult to analyze. Okay, so you might ask why do we want to use recursive? Okay, so why not just use loop? There are certain problems. Okay, there are certain problems which are more naturally implemented using recursive. Okay, more naturally implemented using recursive. Most of the time, I think most programmers prefer to use loop instead of recursive, because when sometimes it is quite hard to imagine things in a recursive way. Okay, but there are certain problems later on you'll see, especially on problems where you use a divide and conquer solution, one of the strategy that we will be learning later on. You'll see that using recursive is more natural to solve the problem. Yeah, sorry, what was the comment? Suppose the increment step is I plus 4 instead I plus 1. What is the time complexity for the loop version? I plus 4. You mean this? You mean this one is I plus 4?
Yes, sir.
What do you think? Yeah, what do you think is the time complexity? Others can help out. Jin Wenhua, yes. Teo Ken Boon said yes. Okay, big O-N, correct. Whether this is I plus whatever, this is still, this is still, okay. Even this is I plus 4, it is still big O, N. Okay. Why? Because we are considering n when n is very big. Okay, when n is very big, no matter here you increment 1, it is still big O(n). Okay. Okay, thanks for helping out. Okay. Okay. So for recursive, okay, for recursive, maybe maybe I delete it first. Okay. If you look at here, okay, if you trace, okay, let us trace the recursive. Okay, let us trace the recursive. Let us count. Okay, let us count the time complexity. We can also count. Okay. Okay, we can count. So 0 and 10. Okay. Let us start counting. Okay. Let us start counting. So n is 3. Okay, n is 3. So what happened is we perform 1. This is plus 1. Okay, plus 1. Plus 1 here, right? 1 will do a comparison, do an addition, do a assignment, do a plus, do a assignment. 1, 2, 3, 4, 5, and then call the recursive, right? 1, 1, 2, 3, 4, 5, 6. Okay. And then we can count, can count 6. Okay, there are 6. So when I is 0, j is 10, we pass in 0 and 10, right? So there are 6, okay, plus 6 primitive operations, okay? Count the operations, right? Just like this, we just now count, right? We find out it's big O n, right? So we can count. Now it increment, okay? This this one is over here. Okay, when we pass 0 and 10, we perform a comparison, then we perform increment, assignment, increment, assignment, and then call recursive plus 6, right? Plus 6. Then I become 1 and j 15. And then n still remain 3, right? I is equals to 1. So we perform again plus 1 plus another 5 plus 6 again. Okay. Yeah. Yes, Raji.
Sir?
Yes. Yeah.
I can hear you, sir.
Yes.
I can hear you, sir.
Sorry, can you hear me?
Yes, sir.
Yes. What is your question? You have a question?
I thought you have answered it. Except new one.
Sorry, can you repeat your question?
No, what I'm saying the other time I was asking, suppose I is equal to I plus 4. Is it going to be the same? Then you say, yes, it's going to be the same. Then my question
Yes.
was, then my question is, what of if I is equal to I times 2? Is it still going to be the same?
This one I don't know. Okay, this one you need to do we need to do analysis. I cannot say it if it's time 2 whether it's still the same. If by right if it's by right if we do times 2 times 2, I believe it's still big O n. Okay. So you have to you could do the analysis just like what I mentioned just now. Just follow the basic steps. Okay, just follow the basic step, do the analysis, and then find out certain simple example. Okay, simple example. Sometimes we can look at and then we can say, oh, it's big O n or what. But in most of the time, you have to sit down and do the analysis. Okay, you have to sit down and then do the analysis and see whether it's find out the function. Okay, find out the functions, and then say, oh, okay, from the function is whether it's a big O n or something else, right? So I cannot. It's not that simple. You just I plus something and then is this big O n or big O something? Is if do the analysis, okay? Go through the step by steps that we discussed, and then see what function it is, and then what is the time complexity, right? Okay. Okay. Let's back to this recursive method. Okay. Okay. So you have. Let me see whether I do it correctly. When I is 0, we okay. I should. Sorry. Okay, this one by right is over here. Okay, when initially we set I is 0, J is 10, right? So here, okay, we perform 6 operations, then plus 6 again, right? Plus 6 again. And then finally, when I hit 3, there are only here now, there's only one operation return Z. Now plus 1, okay? Plus 1. Sorry, plus 2. We do a if statement plus 1 return. So plus 2. So from this function, we get is Fn is equals to Fn is equals to, so this 6 is a constant. So 6, how many n? How many 6? We have 3 6. When n, okay, when n equals to 3, so 6n plus 2, okay? So if you so what I'm trying to say is, if you analyze this, this will also give you big O(n). They do the same thing. One using recursive call, one using loop, another using recursive call. Okay, so you get the same time complexity, right? Okay, so now I hope everyone familiar with the recursive. Yeah, do the analysis and then see what's the time complexity. Thanks, Kingbun. Okay, so this the way I analyze the recursive call, you can do it like this. Okay, you can do it like this. Just count like how we do for loop, we can do for recursion. So from how we analyze our analysis of the recursion, what can you conclude? So there are a few conclusions we can do. Okay, there are a few conclusions we can do. The time complexity of recursive depends on what? What is the time complexity of a recursive call depends on? What is the time complexity of the recursive call depends on? Yeah, thanks, Dao. Thanks, Wenhua. Yes, how many times the recursive call is called? Or in another words, what is the depth of the recursive? Okay, what is the depth of the recursive? So in this case, you see the depth of the recursive is 3 times, right? The depth is 3 or 4 times, right? When you hit the 4, it already returned, right? The depth of the recursive call depends on the time complexity of a recursive call depends on the depth of the recursive functions. Okay, and at every node, you can see as a tree structure. Okay, you can see the recursive as a recursive call as a tree structure. Okay, so at every node it performs some task. At every node it performs some task, and when it reach the break function, it will perform some task. You see, This is the break functions or the return function. Okay, the return function. For those who are not familiar with recursive call, a recursive call will always, as I mentioned just now, will always call a recursive call is called recursive because it calls back itself, right? It calls itself. Another feature of a recursive call is it must have a stop. Okay, it must stop the recursive and then return. If your recursive call continue call until no end, you will end up with end of no more memory. Okay, and then your method will your program will just die. Okay, so a recursive call must call itself, and there must be a statement that stop the recursive and then return. Then okay. So these are two conclusions. And the third conclusions that I cannot show you here is, in this example, I only call the recursive once. It is possible to call a recursive more than one time in a method. So I can have a recursive and then call recursive and then call recursive. Okay? It can be done. Okay? Depends on the problem. But this problem does not require me to have more than one recursive call, okay? In the codes, okay? In the codes, okay? So I repeat, the complexity of the recursive call depends on the depth, okay? Depends on the depth and depends, second thing depends on the leaf, okay? Depends on the node, how many nodes or the depth, and then the leaf. Okay, this is at the end the leaf. How many leaf you have? There's only one leaf here, leaf node. And the number of recursive call. In this example, I only have one. It can have more than one. Okay, it can have more than one, depending on the problems we are solving. Okay. Okay, now let me. Please, sir, does recursion have a higher cost? In terms of complexity, I already proved it to you. The complexity is the same. Okay. In terms of the time complexity, analyzing with a big O, then basically it's the same. Okay. Obviously, if you implement it correctly, you should get the same results. Okay. Now, so what I've shown you here is the way to count to evaluate the recursive call, just like using the loop, right? We count and then write the functions. Now let us look at other way to analyze the recursion. Okay. Okay. So mathematical inductions. Recursion is like mathematical inductions. There is a base case, okay, and there's an inductive steps, okay. There's a base case and there's an inductive step. Okay, let us look at what does it how we put the recursion in that form. Okay, in mathematics, recurrent relations is an equation that recursively define a sequence. Each terms of the sequence is defined as functions of the preceding terms. Okay. So recurrence relations, also called recurrence equations or recurrence, is a natural way to determine the complexity of algorithm based on recursive strategy. Okay. So okay. So now let us look at this piece of code. So it's similar to the one that I just showed you, but I left out some, make it simpler, okay, so that we can see how to analyze it. Okay, let us see how to analyze it. Okay, so actually recurrence relations is one way. Another approach is actually called recurrence tree. Okay, so this is what we call the recurrence tree. Recurrence tree. Okay, recurrence tree. So this is the recurrence tree. Let me show you the recurrence tree first, because it's simpler. So the recurrence tree, so we have these recursive functions, right? We input n. So okay, then recursive. Normally we use, actually normally we use tn. Okay, normally we use tn. Yeah, just put recursive. Okay, so sorry. Okay, so normally we use tn. Okay, look at, so when okay, and oh, okay, when let's say n is equal some value, okay, n is equal some value, so some value which is not 0, let's say 10, okay, let's say 10, let's say n equals to 10. So what happens is you do a comparison, and then obviously this cannot be true, okay, this cannot be true. If true, then it will straight away end already, okay. If this statement here, if this condition here is true, then it straight away end. So we look at what happens. So n equals to 10, 10 is not equals to 10, not equals to 0, then we execute this statement, right? Then we execute when, and then we reduce minus n by 1. Now n becomes 9, right? Okay, now n become 9. Then, okay, now we call recursive. Okay, now we call recursive. We call recursive. So when we do that, we assume there are C constant number of operations performed. So if you want to count, you can count. So 1, 2, 3. Okay, 2, 3. You don't plus 2, 3. Okay, so there are 3. 1, 2, 3, and then the recursive itself 4. Okay, so C is 4. Okay, if you want, you can put a 4. Normally, normally what we do is we either use a C or some other character, or even simpler is +1. So most will just put +1. For instance, if you look at some reference, they'll just put +1, +1. Just 1 is just represent a constant. Okay. So next, if n is 10, then next will become 9, right? But if it's n, then the next time it will be n minus 1, right? Again, then again n minus 2, and so on until n equals to 1, and then n equals to 0. When n is equals to 0, something different happen. Then our constant now become 1 plus 2. Okay, 1 plus 1, 2. So here now we stop. Okay, stop return. Okay, so if you want, you can just simply put as +1 or some character or +C. Doesn't really matter because these are all constant. Okay, these are all constant. So what happens is if you analyze the depth of this is n plus 1, and this is all constant. So from this recurrence tree, we can see that this is big O n. Okay, so this is a simpler method to analyze recursive, okay, to analyze a recursive function, okay. Okay, I will explain the third method. Okay, I explain the third method. So the recurrence tree. Okay, so recurrence tree, nice is you can draw the tree. Okay, then look at the depth, look at each node, what is the complexity, right? And at the leaf, what's the complexity, right? Then you can conclude, okay, this is big O n. Right? So quite simple, right? The third method is called the recurrence through the recurrence relations. These functions, okay, these functions, when n is equals to 0, when n is equals to 0, the complexity, the equation is Tn equals to 0 equals to d, okay, equals to d. We take d primitive operation. As I said also, if you look at most of the reference or book, you will just put a 1, okay, or put a C or some characters, okay. Most of the time you see is equals to 1. It just represents a constant, okay. When n is equal to 0, so it takes constant operations. But if n is not equals to 0, okay, so this part is n is not equals to 0. So in or n more than 0 actually, okay, n not equals 0 or n more than 0. So what happens is Tn here, Tn, okay, Tn equals to n minus Tn minus 1 plus some constant, okay. We every time what happens is we minus 1, we represent this Tn with Tn minus 1 plus C, okay, Tn minus 1 plus C. Every time we, for this recursive, every time we minus 1, and then we also at the same time perform a C constant number of operations, okay. So this is the recurrence equation or recurrence relation. So what can we do with this? What can we do with this? Okay. So let us look at what we want to do is look at the sequence. Okay. Let us look at the sequence generated. So we show that Tn is equals to Tn minus 1 plus C. So when it's Tn minus 1, what we get is Tn minus 2 plus C, right? Tn minus 2 plus C. When it's Tn minus 2 plus, when it's Tn minus 2, we get then Tn minus 3 plus C, okay? So basically it's, as I said, normally we use Tn here, okay? So from Tn, we get Tn minus 1, okay? So look, okay, so Tn equals to Tn minus 1 plus T, Tn minus 1 equals to Tn minus 2 plus C, 2n minus 2 equals to Tn minus 3 plus C, and so on, until you can do it until T1 is equals to C, and then another thing is T0 is equals to D, right? T0 equals to D, okay? Okay, now we use the substitution rule to find out the time complexity. So look here, Tn is equals to Tn minus 1 plus C, right? Tn is equals to Tn minus 1 plus C. What we know about Tn minus 1 is Tn minus 1 is Tn minus 2. So we replace this inside. Okay, we replace this inside. So we end up with Tn minus 2 plus C, right? Okay, now what is Tn minus 2? Tn minus 2 is this one. Substitute it inside. So that is called, that's why we call the substitution rule. So now look at the pattern. This one can be put as Tn minus Tn minus 3 plus 3, right? So if you want, just put 3C lah. No problem. Okay. So what can you so if you continue, meaning if Tn minus k is if we replace by some k, okay, if we replace by some k, meaning then this part will be k times c. Okay, this part will be k times c. So now assume k equals to n. Okay, now we assume k is equals to n. Why we want to assume k equals to n? Because when k is equals to n minus n, we get T0. And we know T0 is equals to D. Okay. So we know T0 is equals to D. Okay. And then k is equals to n, right? Replace k with n. So n c. So d plus nc. So the time complexity is big O n, right? Because d is constant, c is also constant. Okay, so this is through recurrence relations. Okay, we can find the time complexity through this substitution rule. Okay. Can? So maybe I think we have for recurrence we have looked at 3 methods to analyze the time complexity. First is just count. Okay, it's just like the loop, we count and then find out the functions, then find out the big O, right? Second method is through this recurrence tree. Okay, through this recurrence tree, we look at how many operations performed at each node. Then we conclude. And the third method is this through recurrence relations. Okay, so I think we have an earlier end of our class today, so that you can process a bit, because today we have touched on many topics, Amortized Analysis, and then analyzing the time complexity of the data structures earlier on, and then for recurrence, for recursive, we have looked at these 3 methods. So look at these 3 methods. Okay, look at these 3 methods. You can understand how these 3 methods are used in analyzing the time complexity of recursive method. Okay, so for recursive method, we have to have a taken special care. Okay, because it is more complex. Okay, it is more complex to analyze it. Okay, Ken, take some time to process how we get this recurrence relation, especially as it is slightly more complex. Okay, and if you have questions, you can ask, or you can also go back and then look back, and then we can discuss again. We will look at more example next week. Okay, we will look at more example how to analyze recursive method next week. Okay, there are few examples that we can look at and then learn how to analyze recursive methods. Okay, we'll continue next week. Okay, any questions so far? I hope you still can follow. Okay, I hope you still can follow. Okay, maybe we end our class. You later you process a bit what we have discussed, and then we could have a we will have a discussion and further discussion on this recursive methods and analyzing them using this recurrence relations, using recurrence tree, and also the typical methods in next week also. Okay. Everyone still there? Okay. Then we end our class earlier. Take a look then, so that next week when we discuss more example, you could follow. Okay. Thank you very much, everyone. Okay. Thanks, everyone. Have a nice evening. I will see you all next week. Okay. Thanks. Bye.